So what do
The
we
next
do?
speaker is Rami Zamir from Tel Aviv University.
And
okay, yes.
נראה, איפה הוא שם את זה? אמור להיות זה.
זה?
כן, נראה מוכר.
איזה יופי של פוט.
Okay, so good morning everyone, and thanks to Rudiger for saving me for jumping over the cliff. I was almost there. And I will talk this morning about something completely different, source coding and different slice. Do you think that the information theory and practice are related? I guess that people that came to this workshop believe so, otherwise they wouldn't come. But in some places I think that some people maybe don't believe so. So I want to, in this talk actually, to connect between two things. One is a very theoretical problem in source coding, which is known as multiple descriptions, considered as a theoretical problem, and Sigmadelta Modulation, which is something used in practice, even in compact disc players, the ones that are saying 1-bit D2A conversion are using such a thing. And I hope I will convince you that in this, under this topic at least, there is a connection. So, let me see. No. Okay, so today there is a very heavy traffic over the internet of mainly of multimedia stuff, video, music. People are downloading things, uploading, or there is a peer-to-peer communication, very heavy stuff. And some of this stuff that is being transmitted is not for immediate use. So you can take a movie from somewhere in the internet and wait several hours, and then you can play it later. But some requires immediate playback, and there is an issue of delay. This could be fine if the network was perfect, but unfortunately, the internet is a lossy packet network. So pieces are lost on the way, or sometimes just are experiencing large delays. Every packet goes through a different route, and if we want immediately to show it, or to hear it, we have a problem of a conflict between delay and reliability. Either we will hear something quickly but with holes, or we will wait, and we will experience delay, and then we can maybe get the lost thing. So what are the options that we can do? One option is to use error control. So we heard the talk about channel coding. You can take several packets together and have some code which allows us, for example, we expect a 20% loss of packets, allow us to recover any 20% which is missing. But then the price is that it is a worst case design. So suppose the network is perfect, so we needed to increase the redundancy by 20% just for nothing. The other option, which is very common, is using of feedback. So I'm waiting to see if a packet arrived. If I get an acknowledgement, everything is fine. If I get a knock, which means I didn't get it, then I will transmit it again. But as I said, there is a problem of delay. Also, there is a problem of a multicast situation. There are many users maybe hearing the same thing. Each one is sending a different acknowledgement. For that, there is a solution. Maybe somebody else here could tell you, Meir could tell you a lot about it, rateless codes. But again, there is a problem of delay whenever you want to get feedback. So people in source coding about 30 years ago suggested a different approach. They said, suppose I need, even in an open loop situation, I don't get any feedback. I want a system a coding system for a source such that whatever I get, I'm happy. If I get, suppose, 2 packets, I get one of them, I'm getting distortion D1, which is okay. If I get the other packet, I get distortion D2, which is also okay. If I get both of them, I get a better distortion D0. I am even more happy. But I can do something with whatever I get. I don't need to wait for acknowledgements and retransmission. So it's a kind of diversity in source coding, a scheme that, or idea of using diversity in source coding. And a student of mine in a class that I taught it several years ago, he suggested to think about the situation where I'm going taking an over-Atlantic flight, so I'm allowed to use two luggages. And in some flights, you don't know if you will get both pieces or only one, and you have the brush and the toothpaste, and you decide which one you put in every luggage, and maybe you will be happy with what you get. So the formal name for this problem is multiple descriptions, as I said earlier, and there are many people who contributed since the 80s. I don't have enough time to go over all the history, but we will see some of the contributions in the examples I will show you. So how do we do quantization? Source coding is basically quantization. How do we do quantization under this scenario? So one approach which is tempting is to say, okay, suppose, for example, I have 16 quantization into 16 cells. They are described by 4 bits. There are 2 bits which are the most significant bits, which gives me a coarse description to where the source sample is. And there are the less significant bits, the other 2, which refine my knowledge about where the source sample is. So suppose I'm sending the MSB in one packet and the LSB in the other packet. If I'm getting the MSB, I'm getting distortion which is roughly, if it's mean square distortion, I'm getting a distortion which is roughly square of this delta of the coarse interval that is specified by the MSB. If I'm getting both of them, I'm getting even finer, which is the small delta. I don't know if you can see that, but it is written here. But what happens if I get only the LSB? Then actually I have a problem, because if I get, for example, 0, 1 in the LSB, I don't know if I'm here or here or here, so I have a large ambiguity. Basically, the distortion I can get is like the variance of the source. So this situation corresponds to what is known in information theory as successive refinement. There is one packet which is critical, this is the MSB, and another packet which makes me more happy. But I'm not interested in the situation when I'm getting only the refinement packet. But this is not what we wanted. We wanted to have a code where each packet is self-contained in some sense, and when I'm getting both of them, they act as complementary. They give us complementary information. So there is another approach, which is called staggered quantization. So I'm using 2 quantizers, which are basically the same. They give coarse information, but I'm making them complementary by shifting one of them with respect to the other. So if I'm getting only one packet, I know the resolution is like this size. But if I'm getting both of them, the intersection size is half smaller, which means that the distortion would be 6 dB better. 1/4 of the mean squared error, because I'm dividing by 2 and taking square. So the happy guy would say, okay, this is good because I'm getting improvement of 6 dB. The pessimistic guy would say, okay, I'm doubling the rate, I'm sending 2 things of the same rate, and I'm only improving by 6 dB. This is not enough. Suppose the situation is that in most cases I'm getting all the packets. So I want to design myself mainly to the situation where I'm getting everything, and only with lower probability I'm less putting emphasis on the case where I'm getting one packet. So how do I do that? Vaishampayan, one of the names which I mentioned earlier, provided a generalization of this staggered quantization approach. He said, okay, let's divide the line into small intervals. Each small interval gets a number. Let's put the numbers in a matrix such that the columns is specified by one packet, and the rows the row is specified by the other packet. So if I get 2 packets, there is one intersection, I know the information with high resolution. But if I'm getting 1 packet, I have a group of small intervals, and I have some ambiguity. And he suggested to do it in a way that there is several diagonals in the matrix which are filled, and the rest are not filled. And this way, the ambiguity when I get only 1 packet is not too large on one hand, but on the other hand, it's large enough so I'm getting a good trade-off between the rate and distortion in each situation. And you can see here the picture of getting 1 packet and the other. The intersection of any 2 is always one small interval, but in this case, if I'm getting 1 packet, my ambiguity is something roughly as 4 small intervals. And in general, Vaishampayan showed that the ratio between the central to side distortion is k squared, where k is half the number of diagonals here, which I am filling. So this is a nice idea. Again, the happy guy would be, okay, but the bad guy would say, okay, how good is it? Is it optimal? And the question is, what is optimal? And in the early 80s, when the problem was invented, 2 years after that, people came with a solution for the best rate distortion performance. I have rates R1 and R2, and I have 3 distortions: side distortion 1, side distortion 2, and central distortion. And there is a certain formula which doesn't look very friendly. And it's not important for us. Maybe we can look on a simplification of the formula for the case where I'm working in high resolution conditions and a symmetric situation where R1 equal R2 equal R and D1 equal D2 and is much larger than D0. In this case, it turns out from these formulas that the product of the central distortion and the side distortion is constant and is independent of the trade-off between how important is each one of them. And then I can think about there is a certain parameter alpha which goes between 0 and 1, and it tells me how much better I am when I'm getting both packets. I'm getting here in the exponent 1 plus alpha, and how much worse I am when I'm getting only 1 packet. Okay, so if this is the optimum where the index assignment in the matrix is standing, Vaishampayan showed that the loss is about a quarter of a bit per description, or 1.5 dB. Again, the happy guy would say this is great, but the bad guy would say, okay, but what are the disadvantages? So one disadvantage is that it's hard to close this gap. It's hard to generalize this idea into vector quantization and thus get rid of these constants. Another problem is it's hard to use it for sources with memory. So many sources are, it's not only quantization of one sample, but there are a sequence of samples which are dependent, like in pictures, in video, in music, and this is hard to generalize the scheme or to embed it in such a system. And in general, it's a non-conventional approach. It doesn't fit into standards. So what do we do in conventional quantization? To close the gap of between scalar and infinite dimension, between scalar quantization and Shannon, you can say we use lattice codes or trellis codes or tree structured codes, maybe one day polar codes. And to close to get the diversity feature, usually in practice people are using oversampling and interpolation. You just sample the information faster, and then you get redundancy in the sense of signal processing. More samples of band-limited source, and then if you are losing some samples, it's not such a bad idea. But maybe this idea is too simple to close the gap to multiple descriptions. I want to show you that, in fact, it's not too simple. And for that, let's go briefly over the main ideas of source coding in practice. So the basic idea is PCM, pulse code modulation. You take a waveform, you sample it uniformly, and then you quantize each sample, and you send the bits. This is good for Nyquist sampling, and assuming the source has a flat spectrum on the bandwidth, so there is no dependency between samples, and assuming the source is uniformly distributed in the range of the A to D. But what if these conditions do not hold? We can use entropy coding, we can use prediction, which I will talk in a minute, and we can use noise shaping, which I will talk in 2 minutes. So how to use prediction? This is the famous DPCM, differential pulse code modulation. In DPCM, we say, okay, the source has memory, and I can predict the T sample based on the previous P samples. So it's a P order predictor, and I'm getting improvement of the variance. The variance, instead of having the variance of the source, I get a smaller variance, and I want to use it in the PCM idea, and the idea is to take something which is inspired by taking the difference between samples. I'm predicting the next sample based on the previous samples, and I'm taking the difference between my prediction and the new source sample, and I'm only quantizing the innovations. The innovation signal is weaker by this, how much this quantity is smaller than the variance of the source, and so for the same number of bits I'm getting better distortion, or for the same distortion I need less bits, and this is how I'm gaining. And this would be good for Nyquist sampling of a source with memory. But in practice, people like to use faster than Nyquist sampling, oversampling. This is the main reason is to trade off between accuracy of A to D, which is expensive, and time resolution. I'm willing to spend more on sampling and less on doing A to D. And a simple way to present this idea, which is called, by the way, delta sigma modulation, is in this picture. So I'm taking a source, I'm oversampling it, so now I'm having samples which are faster than Nyquist. I'm quantizing the source, but what I'm doing, I'm taking the difference, the delta between the input and the output of the quantizer. This is the quantization error. And I'm taking this error basically as it is, or maybe multiplied by some positive constant, which is smaller than 1, and I'm subtracting it from the input in order to get the next sample to quantize. So this is the recursion that we are assuming here. If we are assuming that quantization is similar to adding noise, which is a very familiar model, then we can do here superposition, forget about the input, and look only about what happens to the quantization error. It goes through this path and returns here with a minus. So I'm getting this picture, simple filter that sees the quantization error, and you can see that the equivalent error is given by minus the previous one, plus the new quantization error. And if quantization error are like IAD process, then you can see that this is an autoregressive model, and because of the minus, it is a high-pass model. So the noise is more in the high-pass part of the spectrum. Now I'm putting low-pass filter and going back to the sampling, original sampling rate, and the low-pass filter will remove most of the noise. This is the nice idea of sigma-delta modulation. This is what happens when your kids are seeing that you are drawing pictures on the computer. And here I'm just showing that even if quantization noise is not additive, you can put a DC signal and calculate what happens in this recursion, and you will see that the error that you get, the error signal is like high pass, although the signal is not changing. So this phenomena is also true for deterministic quantization. And here we see in the spectral domain what happens. So the source is upsampled by some factor, and then the source occupies only a small portion of the spectrum. And then we are doing this delta sigma. And I'm putting here some general noise shaping filter, not necessarily what I showed before. And so the noise gets some high-pass spectrum over the entire band. And then after the low-pass filter, I'm I'm left with much smaller noise than I started. The distortion would be only the integral only over the in-band part of the spectrum, so that the oversampling gain is the ratio between the total noise and the in-band noise. And people are using Sigmadelta, as I said, mainly for trading off resolution of A to D with time resolution. Also, in the CD player, what you get is that by oversampling, the problem of aliasing is less severe, and then it is easier to remove, to do the anti-aliasing filter, and this is why it is used there. And also, at least in military situations, I know that it is used to combat errors and erasures. And this is exactly the feature we want to use for multiple description. So let's go back to multiple descriptions, the problem we started with. And suppose I want to solve the problem of two packets that I described originally. So there is a source which is oversampled by a factor of 1/2 and interpolated, of course. And what I'm doing, I'm doing quantization using something which I called here ECDQ. And those of you who do not know that, I will explain later. It stands for entropy coded detailed quantization. I'm taking the quantization error and feeding it back using a noise shaping filter. And okay, this is usual delta sigma, basically. But now I need to build from the oversampled source two packets. So I'm doing it in a simple way. I'm taking the even samples, putting them in one packet, and the odd samples in the other packet. Since I oversampled by a factor of 2, each subsequence is good enough for the source if we didn't have noise, of course. That's Nyquist sampling. And if I get both packets, if I wouldn't have noise, then I don't need it. I'm getting twice what I need. But let's see what happens with the quantization noise. So there was a noise, as we showed before, which is more like a high pass. If I'm getting only one packet, it is equivalent from the noise point of view to doing subsampling or decimation without doing before that anti-aliasing filtering. So I'm getting the folding of the spectrum of the noise into the in-band, and I'm getting high distortion. If I'm getting both packets, I can do the perfect low-pass filtering and forget about the high-pass noise. And in the language of multiple descriptions, this means that the ratio between the distortion in the side decoders, the one that gets only one packet, relative to the distortion in the central decoder is exactly the oversampling gain of the delta sigma modulation. Okay, this looks nice, but how it compares to, we want to see how optimal it is. So before that, what is ECDQ? I mentioned entropy coded detailed quantization. In general, ECDQ means that I'm taking a source, a discrete time source. I want to do vector quantization using a lattice quantizer, but before that, I'm dithering. I'm using a noise, additional noise, intentional noise, before quantization, and after in the reconstruction, I will subtract this noise again. So it's not a real noise; it's a pseudo-random noise. And I'm also doing entropy coding based on knowing the dither. So again, this is a known quantity. We don't have time to get into the details, but I will tell you the properties of ECDQ. One property is that the quantization error is independent of the input. And this is due to the dither. The other property is that the rate of the quantizer, the entropy rate of the quantizer, given the dither, is simply the mutual information between the input and the input plus the dither. So a mutual information is something which maybe look frightening from a practical point of view, but for analysis is very friendly. So this is a nice thing. And the other thing is that if I'm now using here a lattice of high dimension, instead of scalar lattice, then the quantization error, instead of being just uniform over an interval, it becomes white Gaussian noise. And this allows me to close the gap of what I showed before, the quarter of a bit, which is the penalty for using scalar quantization. But anyway, the ECDQ is not so important here. It's just important to understand that the noise is really additive when I use detailed quantization. And here I give you a picture of what we discovered as the optimum noise shaping for the delta sigma for multiple description. And the optimum noise shaping turned out to be this two-step spectrum. So I have one step in the in band and another step, flat step at the out band. And due to rules of filters, these are minimum phase filters. It turns out that the product of this height and this height is fixed. This is the second moment of the quantizer, which is a lattice quantizer. This is why I denote it as sigma lambda square. The product is fixed, and the ratio between these two heights determines the ratio between the central distortion, the D0, and the side distortion, the D1 or D2. The rate, as I said, is given by a mutual information formula, which at high resolution is half log the variance of the source divided by the variance of the quantizer. At non-high resolution conditions, the formula is a little bit different. But in any case, this allows me to do a computation, and we get to the main result, which is maybe surprising. And the result said that if I'm using this two-step filter, which requires infinite dimensional predictor or filter order, and if I'm taking the dimension of the lattice in the ECDQ to infinity, then this delta sigma ECDQ scheme achieves the optimum performance for symmetric multiple descriptions. So I'm closing completely the gap to the optimal performance. And for me, the nice thing was that this sigma delta idea translated a theoretical problem, which in information theory, it requires using random codes and joint typicality decoding and all the things that we know from information theory, just to signal processing ideas, simple signal processing ideas. And one nice feature is that the quantization is basically a conventional quantization. We don't need to do this grouping of intervals, so we can see more clearly how this can enter practical schemes. We can think about the oversampling in general as taking a source, even an IID source or a memoryless source, and transforming it into a sparse signal in a higher dimensional space. This is what we did by the oversampling. The noise shaping makes sure that the noise, most of the noise, is going to those dimensions where the source doesn't exist in. And this allows me to get better central distortion relative to side distortion. And the lattice ECDQ, the lattice is used just to move from scalar performance to high dimensional, to this Gaussian performance, which are required for theoretical results. Okay, so it could be a nice point to stop, but I have a few more minutes, so I want to tell you a little bit about extensions. And this is more recent. So what I described before is a work with Jan Ostergaard, a guy from Denmark who came here 3 years ago as a postdoc. And since then, there were some developments. One is, I mentioned, what do we do if we have a source with memory? We would like to use this scheme also to encode sources with memory. Another extension is what to do with more than two descriptions, and the other one is what to do with more general network topologies. So let me tell you briefly about each of the problems. Regarding memory, so as we saw, the approach to sources with memory in practice is to do DPCM, differential pulse modulation, or prediction. It turns out that it is possible to use two loops in the system. One loop which is responsible for prediction. This is the DPCM loop inside here. And another loop which is outside this is the one which is responsible for noise shaping. It takes the input and the output, take the delta noise shaping and feed it back. And it turns out that if you are using DPCM in the right way, and you have two loops of DPCM each one is responsible for each one of the packets, then you can approach as close as you like the performance which are promised by information theory for encoding a Gaussian source under mean square distortion, and the source can be with general spectrum, not necessarily white source. So this is the approach to the memory problem. What about more descriptions? This turns out to be a tricky problem. Consider 4 descriptions. So just extending the idea, instead of oversampling by a factor of 2, we will oversample by a factor of 4. We will have a certain spectrum, and we can now examine what happens if we get any subset of the descriptions. If I'm getting every fourth packet, which amounts to subsampling by a factor of 1/4, then all the spectrum will collapse on the in-band, and we will get high distortion, full aliasing. What happens if I get every second packet? This amounts to uniform sampling, which is less than needed by the entire spectrum, but better than what needed by the source. It turns out that we will get only collapse of this 3 on 1, and this will contribute to the distortion. The 2 will stay outside by the low-pass filter. And if I'm getting all of them, I can stay only with this part of the spectrum. This is fine, but what happens in multiple descriptions? I can get any subset. So what happens if I get 3 out of the 4? Or what happens if I'm getting two packets out of the 4, but with non-regular pattern? I'm getting 2 packets, and then I'm not getting anything, and then another 2 packets. Then this corresponds to non-uniform sampling. And non-uniform sampling doesn't have a simple solution, and you cannot just simply look on the spectrum and analyze the result. For this problem, we only have partial results with a student, which is, I'm sorry, by the way, I didn't mention the one who contributed to the work on the DPCM. This is Yuval Kaufman, who is sitting here. And another student who is sitting here, Adam Mashiach, investigate the case of what happened with more than 2 packets. There are some partial results. How am I with time? Some of the results are encouraging. Some of them show that maybe we need to do something more clever than just oversampling uniformly in time. And the last point I wanted to mention, what happens in more complicated scenarios. So the regular multiple description problem corresponds to single hop network. So there is a source node, I'm transmitting packets, some of them arrive, some of them do not arrive to the sync node, and then I'm using a multiple description code. But what happens if there are routers or switches on the way, and each switch may experience a situation where the capacity it sees at the output is smaller than the capacity it sees at the input. A simple switch or router would, in this case, would just discard the packet, would say, okay, I cannot transmit it because the capacity I have at the output is smaller than what I need. A more clever solution would be to use a modular code, which is not only a multiple description code, but also a successive refinement code. So each packet would have both a coarse part and a fine part. If I'm arriving to a point where the pipe is smaller, I'm throwing away the fine part and I'm only sending the coarse part. But still I'm keeping the multiple description feature so that any combination of packets either at this point or later from only with the coarse parts will give me something which is good. And these results were established together with another student, Tal Be'eri, and we show that basically, if you do it right, you can achieve optimality in all the situations. Time to summarize, or maybe to say a few morals that I think I would like to keep from this work. One is that ECDQ is a nice tool. It simplifies the analysis of many schemes or scenarios. and allows you to get a nice result, which you cannot see if you just work with the regular codes, regular quantization, which are schemes which are non-linear and are complicated to analyze. Another thing I would take from here is the fact that structured solution doesn't mean that you lose performance. Sigma-delta modulation is a scheme with a structure which is very different than random codes and, as I said, joint typicality encoding and decoding. And we can see here, like in other occasions, that structure can take you all the way to the optimum. And the last thing is that there are still very interesting questions about more than 2 descriptions, which are still under research. So thank you very much. And there is time for questions. I think there is nobody to manage it here, but okay. He's here. Okay. Yes, ma'am. Yes, ma'am.
I see that the trade-off between the sample distortion and the side distortion comes from the filter choice.
Mm-hmm.
You try to sort of trade off between the noise shaping outside the band and what happens when it's alias inside.
Yes.
But what about and you presented some solution, but how sensitive it is? I mean, how accurate you have to make those filters in order really to get what you promised us? Yeah,
because in order to get the 2-step, you need the infinite order filter.
Exactly. Usually you use filters.
Yes, a good question. So in this 2-step solution, we have only one parameter, and with that we sweep all the possible ratios between side and central. Now you say we have more parameters. I think the behavior should be, I don't think it should be very sensitive, because the only payment is how, okay, I mean, in the paper, we have a certain bounds that we developed. We showed that a minimum phase filter with 2 steps is optimal, and at each step in the bounding the sequence of bounds, you can see how much you are losing in terms of the trade-off between rate and distortion. So I don't have it clear in mind here, but I believe that it is not very sensitive.
And if you use standard noise shaping filters,
like what? Like depending on.
Like the one that you've shown.
In the beginning with only one tap.
Yeah.
It's a good question. I can't give you but I don't think the solution is very sensitive. But it's a nice thing to check. Right. By the way, something I want to mention, if there is not any other question, Sigma-delta modulation is known as a hard problem because of the nonlinearity of the quantizer. And then people didn't try to go beyond the first order prediction, because it becomes even more complicated and there are issues of stability. But with the dithering, everything is nice. Although maybe it's a little bit of a cheating, but because we average over, all the possibilities of the dither, but it simplifies things. So I really wonder if in delta sigma modulation, in practice, even without multiple description, dithering can, makes the system more stable, allow to increase the prediction order without paying anything. So I think it's another thing to consider.